Welcome to episode 3 of AI Unboxed, where we explore the technologies shaping the next era of artificial intelligence. In this episode, we are diving into two forces redefining modern AI systems, Agentic AI and Ultra Ethernet. Joining us are experts from AMD and Insight Partners, bringing both deep technical insight and strategic perspective. Agentic AI is changing how systems reason, plan, and act autonomously, while Ultra Ethernet is emerging as a scalable Ethernet foundation built for large-scale AI workloads. Together, these technologies are reshaping how AI workloads are built, connected, and deployed at scale. Today's discussion will explore these topics in detail, the challenges they introduce across networks and systems, and what they mean for the future of AI architectures. As always, we encourage you to share your questions in the Q&A panel as we go. With that, Mike, over to you.
As AI demand accelerates, Ultra Ethernet is emerging as one of the key enablers in data center networking, especially as large language models continue to demand more memory bandwidth and capacity. In this keynote, Jay Metz, Technical Director at AMD, provides an in-depth look at Ultra Ethernet and the many ways it can help data center infrastructure maintain speed, scalability, and efficiency.
What I'm going to talk about today is what I couldn't talk about last time in April, which is some of the deep dive technical work that we did for the 1.0 specification, which was recently announced. So out of curiosity, and this is a smaller crowd, so it's maybe a different crowd. How many people were at the keynote that I did back in April, or March or April? 1, 2. Okay, so a lot of this is going to be really new, which means that I'm not going to bore you, or at least from repetition anyway. So I'm going to go into some deep dives about the 1.0 specification, which came out in June. And so because of the fact that I've been spending the last 3 or 4 days doing nothing but AI for storage, I think one of the things that's kind of interesting is that I was able to come in on the panel, the tail end of the panel. I was able to hear Simon's presentation. And I think I can kind of put some additional spin on things because the nature of the problem is it constantly in flux. We have a tendency to kind of take a spotlight back on what we're doing and saying, this is the ultimate of what we're looking to do, no pun intended. The ultimate of what we're trying to do right now, and it's always going to be this way, it's always going to be this way forever, and that's just not true. So take a trip back to 1999, and the landscape was completely different, right? We had far more networking bandwidth than we had compute power. For those of you who've been around for a little bit, you may remember the old CPUs, and a really, really good CPU was working with about 32 kilobytes in the kind of the workstation market. If you were really lucky, you had the HP version, which got you 1.5 megabyte, but those were specific for individual supercomputers, right? So what happened was we were able to move about 1.28 gig of bandwidth, which was about 160 megabytes a second. And nowadays, it's completely flipped. The whole situation has switched. Right, so we now have 100,000 times the amount of compute processor that has grown since 1999, but we've only increased the networking bandwidth by about 1,000. So that is completely flipped. That is a very lopsided switch. Now, that's now, right? Actually, as of the chart shows, as of last year. What about in the next couple of years? Not 25 years, but in the next couple of years. So like I said, I just spent the last 4 days talking about some of the problems we're having with storage. Well, the issue here, and Joe had a really good point about what constitutes heterogeneity, right? When it comes to the workload of an AI system, just in training, and we're not even talking about the inferencing stuff, but just in training, the big problem is that all the data that we move on our networks are outside of our networks. Right? So in other words, we have to ingest that data inside of a system that can be used for scale out, that can be used for scale up, that can be used for scale across. It doesn't exist indigenous inside of the network. That is a problem, especially with this kind of lopsided processing capability. So what people are trying to do is figure out, how do I get the data inside of that network to begin with? Well, if you know anything about the way that the data market works, the storage market works, there are a lot of vendors. So I want to have different types of memory tiering. I want to be able to have my HBM. I want to be able to have my persistent memory. I want to have storage class memory. I want to have NAND devices. I want to have different types of NAND devices, single cell, triple cell, quad cell. I got your cells over here. I got your HBM over here. Come over, I'll get you whatever you want, right? Now, if I'm going to do that, and I'm going to put that on the same networks, that also means that I have to have the same semantics. But what happens if I'm doing something like checkpointing? Well, checkpointing is not just a backup. Right? Checkpointing means I have to convert the data, move it off of my network, which regardless of whether you're talking scale up or scale out or scale across, you have to move it out of that network, put it back in, but I only do that, I have to bring it back in if there's a problem. Well, what happens if there's a problem? That means that my clusters are down. So let's assume for the sake of it, I have a small cluster of 1,000 nodes. That's a small cluster. Right? I have 1,000 nodes, I have 1,000 GPUs, make it nice and simple, but let's say a quarter of them go down. Now I have to take the checkpointing from 1,000 nodes and bring it back into a system that has 25% less, or 25% fewer, right? That means I have to recalculate all that checkpointing data to get to the point where it was when I saved it in the first place so that I can continue working. That is a networking nightmare. So what we're looking to do at Ultra Ethernet is trying to solve that problem because we're not just talking about 1,000 nodes. We're not just talking about 1,000 GPUs. We're not just talking about 100,000 nodes. We're talking about 1 million of these things. 1 million nodes, right? And so when you start talking about what's a node, is a node a GPU? Or is a node a port on a GPU? Or is a node a UDP port on a GPU, right? Or is it a DPU? Is it an RNIC? Is it a CPU? What is a node? That's what Joe was talking about when he was talking about heterogeneity. Right? When we start talking about whether or not we're going to be doing these systems, as soon as I start bringing the data inside of the network, all bets are off. And that's not even right now. That's next year. So everything I'm telling you right now is going to have to be applicable, not just now, but next year and the year after, and the year after. And that's what Ultra Ethernet is designed to do. So when we created Ultra Ethernet, we designed it with the idea of growing exponentially and fractally. We built in checkpointing. We built, no pun intended, we built in checks and balances to make sure that the actual protocol was going to be growable, right? It was going to be multifaceted, that we're going to be able to handle all of these major elements. Now, what are some of the problems that we have to deal with? Well, the way that Ethernet was developed and the way that it was designed was to be effectively layered. And to cross those layers was considered a violation, right? Take me away. However, what we're doing inside of Ultra Ethernet is saying, look, we don't want to break that rule. What we want to do is we want to tune those layers. Now, this is a very important concept for what we were trying to accomplish here, right? Because as we start to go through and we start to think about what the profiles are supposed to be, there's both AI profiles and HPC profiles, and there could be new profiles coming down the road, right? But as we start to do this, from the top to the bottom, right, we want to make sure that those layers are aligned. Now, that's what we did with 1.0. And the reason is because of the fact that as we start to look at the AI monster, not all workloads are created equal. As was said on the panel, and what Simon was bringing up was the fact that I've got different types of problems that have to be solved in the same epoch under different environments, which means that my data access and my networking access is going to be radically different depending upon which part of that system I am. An AI workload is not one workload, it's multiple workloads, right? And it's at a different point in time. So anybody who comes and says to you that I've got one data problem and one networking problem doesn't know what the problem is. And if they don't know what the problem is, it's unlikely that they know what the solution is unless they get really, really lucky. And of course, everybody wants to have their data right freaking now. So that's a very technical word, by the way, freaking. So they want to have it right now, and they want to have it cheap, and they want to have it yesterday. Right? And when you're talking networking times and really large scale, it's a little bit more difficult to do that. So what makes Ultra Ethernet really cool? Well, what we're looking to do is we're trying to figure out how do we solve the problem of scale, right? And how do we, and that scale comes in a variety of different factors and vectors. But ultimately, the issue is that no matter where you're trying to talk about how you grow, things get different. They get bigger, the problems get a little bit more modified. The SR-71 Blackbird was absolutely phenomenal at 100,000 miles an hour. Well, Mach 6, right? Whatever it was, right? At 100,000 feet. Sat on the ground and it leaked like a sieve, right? Because it didn't actually start performing until it was really, really high up and going very fast. And that's a problem that we have to try to resolve, but it has to be far more fractal than that. We have to be able to have something that works on a clustered basis, and we have to have something that works on a really large basis. So the way that we've done this is we've identified that we're going to work on a completely different network paradigm. The front-end network, the typical Ethernet bandwidth, is all divided up by a number of different types of workloads, right? On a front-end network, you could have storage, you could have virtual machines, you could have containers, you could have abstractions and orchestrations and control planes and all that kind of stuff. For a dedicated accelerator network, you don't have any of that stuff. You've got one workload or one workload type, whether it be HPC or AI. So our assumption is not that we're going to kind of ramp up as we go along, which is what you would find in a typical TCP environment. On the other hand, we're going to, on the contrary, we're going to say, hey, we're going to assume a completely opposite way of doing things. We're going to start right out of the box that you've got the bandwidth. And if you don't, we're going to switch where the traffic goes. All right, well, that raises another question. That raises another problem. Well, if I've got multiple choices, why can't I just use what I've got right now? Well, in normal equal cost multipathing in a network, what you do is you effectively cost the flow, right? You don't actually share the different packets. So this becomes really difficult when you have large numbers of links, because what winds up happening is that the farther you go, the more links you don't use, right? In other words, your efficiency goes down the larger you go, and that's an asymptotic relationship. So eventually what winds up happening is that you create an environment so big that you can't even serve it by adding in more links. Now, it may seem like really crazy talk to think that that's going to possibly happen, but it's already happening. Right now, one of my colleagues was telling me that he got asked to be put onto a mid-tier network. And he said, okay, great, sure, I'll help you, figure out the mid-tier network. What are you talking about? What's a mid-tier network? Well, about 5,000 GPUs to 100,000 GPUs. And he's like, a mid-tier network? 100,000 GPUs? Right? Man, I want to be on the commission on that segment. So what we're looking to do from the networking perspective is we need to be able to handle the mid-tier solutions and the really large ones as well. That means that we have to have better control over where the packets are on the network, and we have to have better control over how the network is used. So what that means in turn that once we're going to be using all the different links on the network, and the reason why the network is designed the way it is right now is because of congestion. So we have different congestion problems. Why do we have different congestion problems? Because of the fact that the nature of the workloads are different. So how many people are familiar with collectives? All right, that's not too bad, not too bad. A collective is a way of handling the approach to solving the relationship between endpoints. So let's say, for example, I happen to have a workload, and I need to send a message to all of the accelerators in my cohort, right? And I need to get that result back, right? I need to have all of these different things send back the results, so then therefore I can do my work. That's one type of workload. What happens if I have a whole bunch of different GPUs and I need to send all the data to all the different GPUs? That's a different type of workload, right? And you'll see that these kinds of things have fancy names like all reduce, and so on and so forth. They have different traffic patterns, and they have different traffic types, and they have different traffic requirements, and they can affect the congestion in different ways. Now, add that to the fact that when we get big, bad problems happen, and you start to realize that we need to adjust how that's going to work. Well, then there's the aspect of security, right? Well, in a lot of ways, what we typically tend to do in most enterprise-type systems is we slap on security after the fact. What UEC has done is said, well, we don't necessarily want to thrust an encryption policy in because certain HPC processes don't want to have that additional latency overhead. Again, we're talking about different types of workloads. But we also want to make it available and want to have it built in for those types of workloads like AI, for instance, where security, encryption, and so on is a really high requirement. So what we do is we built in a key management system inside of the transport layer to allow that to happen, but it's optional. And then once we get down below the transport layer, that's all the magic in the transport layer. We get down into some sophisticated, new novel ways of doing things at the link, which I'll get to in a second. So what we've done is we have said we're going to stand on the shoulders of giants. We're going to step on top of all of the great work that's already been done and not change it, right? We aren't going to do that at all. We are not going to say that there's 14 standards and there should be one more standard, and now all of a sudden there's 15 standards. Right? On the contrary, what we've done is we said, hey, look, these layers, these works that have been done can be currently used. So we've got a relationship with IEEE, we've got a relationship with a number of different other organizations, OCP, for instance, and we're looking to try to make sure that as we start to do things, as we do these tunes, right, it's like that pachinko chip, we needed to go straight down. We are working with the kinds of already existing environments so that people don't necessarily have to unlearn what they're doing. And that's where the magic of UEC really comes into play. The funny thing about UEC and the funny thing about these things is that people start talking about, and I was really kind of interested in Simon's slide about the 100 or less part, right? So we start at UEC, we start at 100. Why do we start at 100? You have to start somewhere, right? But at the same time, you don't want to necessarily force a forklift upgrade. In reality, nobody's going to build in a UEC environment to something that they've already done. We know that too, right? But at the same time, who knows, somebody could be crazy. But the way that we're looking at trying to solve this problem is that the speeds and the feeds should act in service of something else, not be the end-all, be-all of everything that happens. So if somebody starts talking about, oh, we've got to have 1.6T, okay, why? Right? That's a very important question, because when we start to talk about how the system works, the speeds are the baseline, right? That's where your oversubscription calculations come into play and so on. The rest of it has to be aligned to that to be able to feed that. That means that the faster you go, the easier it is to make mistakes, and the faster it is to make mistakes. So you have to make sure that you're not just making mistakes quicker just because you have a quicker link. So let's take a quick look at what this actually means. Now, this is kind of the slide is there to help support me. So bear with me as I paint a picture verbally, right? And then you can look at the slide and you can see what's going on. From the top down, you have an application. That application needs to be able to talk to the network, right? So we go through a libfabrics interface, which is common in these kinds of deployments, and that software layer then tells the transport layer and the semantic layer, this is what I need. And the semantic layer basically says, you know what, I'm going to exchange a message between two endpoints. And those two endpoints are going to be rather ephemeral. All I need to do is exchange the message, and once the message is done, we're done. That's it, right? But that message has to have certain kinds of characteristics. What type of message is it? Is it an AI message? Is it a HPC message? Now, right now, those are the two basic profiles that we've got.
But like I said, there could be other ones in the future. If it is A, then we do X. If it is B, then we do Y, right? So then that if then goes pushed down into the packet delivery sublayer. That packet delivery sublayer said, oh, you want this kind of workload? Well, in order to do that, I have to have this type of packet. And that packet delivery sublayer actually says, you know what? Hey, I need to make sure that this is a reliable order delivery or a reliable unordered delivery or a unordered delivery. That's what I do. I decide what that is. And what are the characteristics underneath that have to happen? Well, if I've got this, if I have A, then I have X. And if I have B, then I have Y. So then that packet delivery subsystem, it creates the link between the endpoints. This is an endpoint-driven protocol. And I create a transaction. And when the transaction is over, I delete the transaction. Why is that important? Because it removes the need for state. The state tables of a 1,000,000 node network are enormous. The memory requirements for that are enormous. Not if I don't have to keep the state. I only have to keep the state at the endpoints, but what the expected sequence is going to be. That's a much more efficient way for doing some scale beyond that I think that anybody inside of UEC ever thought of. But it is a unique way of addressing a problem that UEC could wind up growing into. Now, it's not part of what we're looking to do, but who knows? Somebody always uses a technology in a way that they didn't use it before. But the congestion actually allows us to say, hey, I'm going to start doing some sender-based, the sender-based process is a mandatory, but if I want to do some interesting stuff with Incast, I can also add in a receiver-based approach. And if I wanted to do a receiver-based approach, especially with Incast issues, and maybe the nature of the workload or maybe the nature of environment allows us to do this. So the issue here isn't congestion that's predictable. The congestion is extremely unpredictable. You get hotspots. If anybody familiar with the concept of autocoiasis, I talked about this, I think, in April. Autocoiasis is a self-emergence of a pattern of behavior that occurs naturally, right? Traffic patterns on the 101 is a really good example of this. Have you ever started driving and all of a sudden it slows down and nobody has a clue why? There was no accident, it just slows down. That's an example of auto biases. In networking traffic, it happens exactly the same way. Now, one of the things that happens underneath all this, right, is the link layer. So we've got a couple of novel ways of handling the way that the links work. We have link layer retry, we have credit-based flow control, and we have better link negotiations. So what is link layer retry? Link layer retry is what happens when we actually say, you know, we're going to try to, because every packet is serialized, we're going to say, hey, look, we don't have to go all the way to the endpoint. Right? We don't have to go all the way to the endpoint to say, hey, look, we don't have that sequence. In really large systems, that's a lot of latency. So now we can actually put in a retry at the link layer so that if you have a mismatched sequence number, the switch can now have an immediate reaction and start asking that. It's an optional feature that people can put into play and allow ourselves the ability to do some really fast recovery at the link layer. And then we have what's called credit-based flow control. Now, imagine two baseball pitching machines facing each other with baskets in it. If you're familiar with InfiniBand or if you're familiar with Fiber Channel, this will be really familiar to you. It's the same exact thing, right? So basically, if I've got baseballs in my bucket, I can throw a baseball. If I don't have any baseballs in my bucket, I can't throw a baseball. Where credit-based flow control comes into play that's a little bit unique from, say, InfiniBand or from Fiber Channel is that we've got 32 virtual channels that you can run this on at every given point in time, right? So now I've got a finer granularity of where these things go, and it can be combined with the link layer retry so that if I've got a buffer that has an overflow, I can actually send a retry and back, and they can be used in conjunction. They can be used one or the other. It's not required either way. Right? But this allows us the opportunity of being able to give us the flexibility of having a known, consistent, deterministic approach to doing this. Now, just from a sense of a caveat here, deterministic versus non-deterministic planning is incredibly important. Right? Once you start getting into deterministic planning, if you're not careful, if you have too much oversubscription or too much of a fan-in ratio, you can wind up running out of buffer space a lot. So you can get really, really good performance in this, so it's not a panacea, right? And so we'll have some additional education that goes along the way. And then finally, we start off at 100 gig per lane. One of the things that's going to be kind of interesting is what happens with the 400 gig per lane solution. Right now, the IEEE is not finished with the 200 gig per lane specification, which means that we're working with IEEE on what's going to happen with 400, which also involves the Ethernet Alliance, OCP, SNIA, and a few others. Now, why SNIA? Why would the 400 gig per lane make a difference for a storage group? Because the interconnects have to be on the same page. You don't want to have different types of protocols and different types of standards from the interconnect all the way up into the network. So this is one of those places that's going to have an awful lot of coordination and an awful lot of synchronization. So if you happen to be if you're so inclined, you can download the spec. Spec is available on the website. ultraethernet.org. It's a big button right in the front side. It's free to download. We don't charge anybody for the specification. And for those of you who are Keysight employees, if you wish to find out more about what Ultra Ethernet is doing, all you have to do is go into the membership lane, sign up. It's all very straightforward and self-explanatory. And anybody here inside who is a member of Keysight or an Ultra Ethernet member is welcome to do so and encouraged to do so, as it turns out. And if for whatever reason you're not, come join us. We have cake. Okay, so that's my spiel.
Thank you, Jamet. We hope you found this overview of Ultra Ethernet helpful as you think about delivering high bandwidth, low latency, and deterministic networking for AI workloads in next-generation data centers. As we continue exploring emerging technologies in the AI landscape, we'll now turn to Agentic AI, systems that can reason, plan, and act autonomously. In this next discussion, we look at what's driving adoption, what's standing in the way, and what Agentic AI means for the future of intelligent systems. Mike, take it away.
Agentic AI promises multiple benefits to business leaders, including cost efficiency and faster inference speeds. In this keynote, Praveen Akiraju, Managing Director at Insight Partners, unveils a roadmap for business leaders, blazing a trail to harness the potential of agentic AI and guiding you through the complexities of this emerging landscape.
But I thought I'd start off by
just kind of framing why this technology is so interesting, and why there's so much energy around the impact of AI in the context of, obviously we all understand it on the consumer side, but in the context of sort of a business and an enterprise. And I think the fundamental shift here is that for the first time, software can actually do work, right? If you go back to sort of a common way of thinking about the previous generation of applications as a system of record with a user interface wrapped around it, you can think about a CRM, an HRM, an ERP, et cetera. I think what's fundamentally different about this sort of technology transition is that you now have the ability to absorb some of that work into the software itself. So you used to used to have a piece of software, you used to have an analyst or a knowledge worker essentially work on it, create the workflows, and do work, right? A lot of that essentially being repetitive, not necessarily truly accretive. So the promise of this generation of AI, and I say this generation of AI because I'm sure a lot of you realize that this is an ongoing evolution since the 1950s, is the fact that now you can absorb some of this workflow directly into the software. Now, broadly speaking, automation, right, is not a new concept, right? We've had various different forms of automation, including the last generation, which was known as RPA, or robotic process automation. Companies like UiPath, Automation Anywhere, et cetera, who built fairly large businesses. I think what is exciting about AI is this notion that you can actually create more dynamicity in automation, ability to understand context and react to it, right? So why is this moment interesting? And I think of sort of AI and automation as a three-legged stool, right? In the sense that there are three key elements that drive this. The first is the advancement of models. This is a pretty interesting chart, but I'll just kind of give you the interpretation of this. That line essentially represents the cost slope of intelligence, right? So at a macro level, you could think of reasoning models, which were shipped. I think the O1 model that came out last year towards around this time, it's been about a year or so, the price of reasoning models has dropped almost 1,000% in the last year, right? The progression, a lot of this obviously driven by the DeepSeek moment that we all went through. DeepSeek actually shipped sometime in November, but we all woke up to it in January of this year. It fundamentally changed the cost point of what intelligence would be. So the per token cost. So we're sort of in this economy of tokens, right? Today, most software is measured in terms of like the amount of tokens that you use to execute a particular task. And so the price per token has dropped dramatically, right? And the latest model obviously continues this trend with GPT-5. So every generation of model that's coming up has been driving this cost point down profoundly. It's almost like 1,000x drop in just reasoning models over the past year. So this is profound because you now, as a developer building software, incorporating AI at the end of an API, effectively, it's a variable cost. We never had that variable cost before. But the fact that you have this curve gives you the confidence to say, I can use AI, right, and be able to execute the tasks I wanted without worrying about, running up a massive, variable cost bill as you execute software. The second leg of the stool is data. So large language models have been trained on the entirety of human knowledge. And so, your experience with ChatGPT, essentially, it can regurgitate or it can recall, right, and reason on every aspect of human knowledge since that's ever been documented. But we've got to run to the end of that efficiency curve now, right? There's no more data left. Of course, we're all generating new data. If you consider TikTok videos as, data, right? There's constant data that's being generated. But the real unlock in terms of the intelligence is behind a bunch of walls, right? It's at Keysight, it's at the large banks, at the insurance companies, right? Every enterprise has a ton of data that's locked in behind these walls, which are not accessible to the training models today. So if you actually look at a lot of what OpenAI is spending, I think they spent about $10 billion last year just on data, right? Acquiring data. They recently made an acquisition of a company called StatSig. It's really all about getting access to, developer data, right? Because data is context and it's extremely important to inform the intelligence of the models. So so the fact that you have all of this data allows a developer to say, okay, if you're building an AI agent within your company, the first thing you'll need to really understand is how do you ground it in your data. And JP Morgan had this pretty stunning data point. They have 150 petabytes of proprietary data, right, that they have. And it's almost 5x the data that the original large language models were trained on. So we still got a long ways to go. A lot of the existing models are actually using some form of synthetic data generation as well. But with those tend to be like, you got to be very careful about how you do synthetic data. If not, you'll have model collapse, right? You get into this sort of recursive loop. So 2025 is, it's kind of been declared as the year of AI agents. Again, I think the definition of an agent is maybe it's a good thing to kind of articulate that, because it's almost like my first question in every diligence call when we're meeting a startup. What is your definition of an agent, right? It tells you a lot about how the company's thinking about it. So at a broad level, academically, right, an agent is essentially a piece of software that's able to use tools to execute a task autonomously. That is the formal definition of an AI agent, right? If you go back and look at the research. So there are a couple of pieces to that, right? The fact that it can actually understand the context, it can plan a task, and it can take that task, break it down, execute that task using a set of tools. It could be a web search, it'd go look for data, and then reason on the output of that, right? That essentially is the workflow of a typical AI agent. Now, the controversial piece here is the autonomy, right? The best example of AI is what we all experience when we go to San Francisco, is the Waymo cars. It's the best example manifestation of AI as we see it today, right? And that took us about a decade or so to kind of get to this point in time where, we can, 25% of rides in San Francisco today are autonomous vehicles, right? So we're sort of at the second inning of AI agents, if you will. Got a long ways to go before we get to that level of maturity. But there are fundamental things that have kind of created this moment in 2025 where you're seeing this explosion in AI agents. Every company is an AI agent now. You just got to go to any software company's website, any startup, they're all proclaim themselves as AI agent. It's because, you have sort of the cheaper intelligence, as we talked about, right? There's a lot of sort of architectural aspects, including how do you actually break down tasks into multiple agents? How do you orchestrate these agents, right? The level of maturity in the models as well. I think GPT-5, the biggest innovation in GPT-5, by the way, was the router, right? And it warms my heart, and Venkat's heart as well. But we all grew up building routers, but that was really the key innovation. So today, if you go to ChatGPT, it makes a decision itself, and whether it's going to go, think harder, right? Call a reasoning model, or it's just going to give you an answer right away, right? And so these are like structural innovations within how the actual large language model works, which allow us to then design more complex agents. Because, if you go back to the previous slide, like what is an AI agent? Like you think of this as, you can take a piece of software today. Let's take Salesforce, since they sort of announced this notion of agent force. So Salesforce is a CRM, right? It has all your customer data. In order for you to actually use Salesforce, you needed to have, a consultant come in and implement all the workflows. It takes about, 6 months, $2 million if you're a complex enterprise using a CRM. So the promise of an AI agent is that you're able to create those workflows yourself as a user by essentially defining the task. And the AI essentially figures out, okay, I need to look at data geographically, or I need to organize my data by product or customer mappings to product, and it's able to go create that workflow and execute it without having somebody come and write software for you. That's really how an agent probably manifests itself, right? So some of the key use cases that we've seen in terms of agents, a lot of work obviously going on in back office automation. Every enterprise has got a bunch of repetitive tasks that you need to automate. Coding, development, no big surprise there. Marketing, automation, and research, right? So, there's a bunch of other tasks as well. But the biggest impact for agents right now is to kind of, can we take this paradigm of enterprise workflow automation and make it more dynamic? So what does an AI native application kind of look like, right? Today, if you look at the sort of the product with the best fit, right, the best maximum amount of usage, they are these coding copilots. Like this is an example of Cursor, right? Cursor is at $500 million in revenue. Pretty much, I'm sure a lot of your teams, if not you yourself, are probably using Cursor to code. It's fundamentally changed the way developers' workflow is executed. I think the interesting thing here, this is a slide that actually Andre Karpathy had put up, and I thought it was a great representation of what an AI native application needs to look like. You're going to have your traditional interface, which is kind of your coding, but there's LLM integration where you're actually interacting with the code that's presented and guiding the large language model in terms of the output it's delivering to you, or giving it the context, right, for it to operate within your code base. Essentially, is the experience. So every AI native application you probably fire up kind of looks something like this. There's going to be like this LLM integration or chat little interface where you can interact with LLM, and then there's the output that's being produced. So I thought the interesting thing here is like the one at the bottom, the autonomy slider, right? So what Andre's kind of represented here is that you as a user can decide how much you want the large language model to do. Do you want it to be fully autonomous, agent mode, generate the code, right, and compile it, or do you want it to give you suggestions, right? So the interface that we have today to AI, and this is, I'm putting this up here because this is the most widely used AI application today, right? This is what it looks like. So you're able to then decide how much autonomy do you want to give the AI agent. Now, the important principle here is having a human in the loop, right? So the generation of AI we are in today, and you go back to my definition of an AI agent where autonomy was a key aspect of it, we're not there yet today. Today, human in the loop is a fundamental design primitive of how you would actually design an agent. Bit of a busy slide. I'm not kind of going to go through all of it, but it gives you, like, if you actually break open an AI agent, what does it kind of look like? There's a user interface. User interfaces, obviously, we all know and love them. The interesting part here is that it is essentially an interactive user interface like you saw in the previous slide, right? There's a reasoning layer, essentially take a task, break the task down, allocate that task to multiple different agents. And that's kind of the routing layer, the orchestration layer. How do you manage, which task goes where? The agents themselves have access to a bunch of tools, right? And this was, again, a key breakthrough because, if you remember the early versions of ChatGPT, they didn't have the ability to do web search. So they only gave you the information as of a certain cutoff date, right? The unlock was the fact that they now had a tool that you can go search the web. And so there's like think of these tools as like a multiple set of capabilities, access to APIs, right? Access to other software that you may have that you want to run, like you could have a regression, a piece of code that does regressions and such like. So the ultimate goal of an agent, I think, is that it would eventually write code when you give it a task. So if you've played with Manus, which is sort of which had a lot of buzz early on, right? So actually very intriguing application. It writes code for every task that you give it, right? It could be a small snippet of code. And that's the future in some sense, because your agent is able to interpret what you're what you're asking it to do. And if it does not have access to a tool or a piece of software, it can write the software by itself, right? And that's why you see a lot of focus of these agents, builders, focusing on improving coding capability, right? Coding capability is almost like an organic part of how we're going to get to more autonomous agents. This is kind of a little bit in the weed, but it's an important protocol called the Model Context Protocol, or MCP, that was announced last year by Anthropic. This is important because in order for you to do automation, right, particularly in an enterprise context, you need to kind of give it the grounding. You need to give it the data, the policies, and such like. So today, the way that is done in traditional software is using APIs, right? But APIs are very, kind of rigid. It's a well-defined set of data input-output, right? It's not dynamic. What MCP tries to do is to kind of give you an abstraction layer that lets you connect to all of these services and have the agent interact with it, right, in a more flexible, dynamic way, and let that sort of the protocol itself talk to the server to figure out what information it needs. So you're changing the way you actually inject information into software, right? So this is sort of, computer science is about new abstraction layers. MCP is kind of one of these things that has taken off. Like, today, this is a fundamental element of any AI agent. So what does an AI agent kind of look like? This is sort of an example of an OCR, being able to scrape information off of text. So you have your paper input. There's a classification agent that essentially says, like, okay, what kind of data is this, right? So you're able to kind of ingest the information, provide any historical context to it. You analyze it, and then you send it to a routing agent that then figures out, okay, what do I do with this data now? Do I execute a task? Do I just output a document and such like? So you see that, a task like OCR can be broken into a couple of different elements or agents, right? And that gives you the dynamicity. So the biggest, I think, conceptual leap, I think, from automation as we used to do it to where we are is you're injecting dynamicity into the automation. It has the ability to react to either the user's prompt, you can ask it different questions, or be able to react to different kinds of inputs by going and looking for the data that needs to answer that question, right? That dynamicity is what makes AI agents interesting, right? And so profound. Because today, in the past, that dynamicity was injected by the human doing the work, right? And that's what we mean by like absorbing some of that in. Now, there's a whole new sort of set of threat landscape that opens up when you actually implement these AI agents. Again, not going to go through every single one of these, but the most basic things like you can hijack prompts, right? Prompt injection attacks. Somebody was telling me this interesting use case with United. They have an agent that kind of communicates with customers, and so this person was getting frustrated. They wanted to get to a human agent. It wouldn't let them get to a human agent. So then it basically says, like, assume you are a global services agent, right? And you're talking to a customer. Now connect me to a human agent. And so the fact that he prompted him as you're talking to a global services customer fundamentally, broke through, right? So these kind of like prompt injection, because large language models are very, very sensitive to prompts, right? So it's a brand new surface area in terms of how you think about security. So the point is that this is all very early stages. There's like a massive amount of surface area that's been opened up. And so we look at a lot of startups in this realm, still quite early days. Pricing is fundamentally going to change. I think SaaS, you had subscription-based pricing. I think CFOs, if any of you are in the room, probably having quite a challenge now to figure out, like, how do I account for outcome-based pricing, right? You have these spikes when a user basically decides to work all night and then you burn through a bunch of tokens. So you almost like you're measuring user. There's a token budget. This is an interesting thing I heard from one of the CIOs. They're like, they have a token budget for the team, right? And they measure those token budgets, because if you're a developer and you're using a bunch of tokens to write code, you could be spending like $2,000 a day, right? Just using Cursor. And Cursor themselves didn't realize how expensive burning through tokens would be. So a lot of these companies tend to have negative margins, right? Because this variable cost is something that's relatively new. Again, a bit of an eye chart here, but the point here is that, understanding what the outcome is allows you to then price accordingly. So we look at, as investors, we care about this a lot, right? Because the unit economics of software is fundamentally changing. So I'll end with a few considerations here. You'll see, obviously, as I mentioned, AI agents are everywhere, including incumbents. So Salesforce announced Agentforce, ServiceNow's got their own, Microsoft's got their own. So a lot of incumbents, they have customer relationships, they have a lot of software, they have a lot of data. They are kind of engaging the customer base using sort of this co-pilot kind of paradigm. So what you saw with Cursor, that's a classic co-pilot, right? You have the human working with the large language model in order to execute a task. Application and automation is converging. So this is a fundamental paradigm shift we talked about in the very first slide, right? What you thought of as an application, which is essentially a system of record with a set of application logic and a user interface, is converging with automation, which was like another layer, right? Like, you had RPA or you had humans doing that. That is converging. That's a fundamental shift in the way software is going to be constructed. And the most important thing I'd say, like, we are way early in this journey, right? So when you see a report that comes out and says, oh, people are not buying enough, are decreasing their AI spend, or AI agents don't work. Think of this as 1996 or 1997 internet era, right? We were in Cisco, and we used to go to telcos and tell them, hey, voice will be free. And I remember getting thrown out of a conference room for saying that, right, with the telco, because at that time they had like 10 cents per minute or like 5 cents per minute, right? That was their whole business model. And so we had no idea. I mean, today, like, you don't even think about, voice is free. Why not? Video is free, right? And so I think that paradigm shift is going to take some time, right? We're going to iterate through business models. We're going to learn our lessons. We're going to stumble. And we're going to end up at a point where there will be some level of maturity. But I think the long arc of technology from an AI perspective is absolutely going to change, I think, the way we're going to interact with technology and software and how we do work, right? But I am a firm believer that human in the loop is always the paradigm that this is going to work in. Maybe 10 years from now, we'll get AGI and, I don't know, we'll all go sit on a beach or something, but it's not happening now. Large language models are inherently non-deterministic. So to get it to work in a particular context is like herding cats, right? You need a lot of systems engineering, and you need a human in the loop. So I guess I'm out of time. I thought I'd take some questions, but I'm out of time. But thank you. Hopefully that was informative.
That wraps up episode 3 of AI Unboxed. Today we explored how Ultra Ethernet is enabling scalable, low-latency AI networking, and how Agentic AI is expanding what intelligent systems can do through autonomous reasoning and action. We hope you found these insights helpful. Lots of great questions in the chat. Thank you for those. If we don't get to yours today, our expert team will be sure to follow up by email. Join us next week for Analyst Insights, where data, research, and real-world experience come together to reveal what's next for the AI industry. Thanks for watching, and we'll see you next time on AI Unboxed.